Alright, gang, here we go. This is for Chem 2 Unit 9. Talking about chemical kinetics. Should be pretty fun here. Alright, so let's have at it. So, chemical kinetics. Alright, a couple of terms that we need to establish just to start, make sure we're all on the same page here. The speed at which a reaction takes place is called the reaction rate. Now, this should make sense, right? Your reaction rate, how fast is your reaction going? And then the study of that rate is called chemical kinetics. All right. Now, this term kinetics, you should think like the pop into your head, kinetic energy, so on and so forth, and you should automatically start thinking about movement, right? Movement. Okay. And so really what we're doing here is in order for a chemical reaction to take place, you need to have these molecules moving, and then once they're moving, they have to collide with one another. Okay. All right. So you get these collisions. Okay, so that's essentially what we're happening is we're studying these chemical collisions, and when these molecules or formula units, ions, whatever they may be, run into each other, they have the possibility of causing a chemical reaction where those bonds are changing, right? You have chemical bonds and then they get broken and new ones get formed. All right. The step-by-step view of this change is called the mechanism. All right. So we're going to start off talking about generally chemical kinetics. How can we control them, and then what are reaction rates? How can we measure them? And then we'll end up this unit talking about mechanisms and kind of diving into those. All right. So let's just talk about these collisions real quick. If in order for a collision to occur, or in order for a reaction to occur, we need a collision, but it can't just be any old collision. It has to be a successful collision. All right, it has to be a successful collision. And there's two things that need to occur for a successful collision to occur. First, they have to collide with the correct orientation. All right, so you imagine these two molecules that are bouncing around, they have to hit each other in just the right way for these new bonds to form. And so if this is our chemical collision, my finger's hitting, when these fingers come together, this is our chemical reaction. We get this new bond right here. If my hands come together, because these molecules, they can't move themselves. They're just moving based on their kinetic energy. They're bouncing off the walls, coming around. And if they hit each other like this, no reaction will occur. If they hit each other like this, no reaction. They have to hit each other like this in order for that reaction to occur. All right, so they have to have the correct orientation, and then the other thing they have to do is they have to have enough energy to beat the activation energy. All right, they have to have enough energy to beat the activation energy, or essentially they have to have enough energy to break the old bonds, okay? And so, like, you have to imagine, like, well, what if my hand was already holding something? It's holding this pen here, and if this other hand coming in, if it doesn't hit hard enough to knock this pen out, then you won't have a reaction. If all it does is come in there, even if it's at the right orientation, but it doesn't come in hard enough, it'll just bounce off, right? And so it's kind of a rudimentary example, but that's essentially what we're talking about. So as we move through the next couple of slides, really what we're talking about is what can we do to increase the number of successful collisions, okay? These collisions are occurring all the time. We've talked about the kinetic molecular theory and how we can take that theory to represent the movements of chemicals and gases and solids and liquids and so on and so forth. Excuse me. All right, so factors that affect reaction rate. Part 1, okay, we'll be talking about these different things for a while, okay, but these are the first 4 that we're going to focus on. Physical state of the reactants, reactant concentration, temperature, and presence of a catalyst. All right, physical states of the reaction. So essentially, if we can change the physical state of them, either what state of matter they are in or their surface area, if we can cause more collections, then their reactions will happen faster. Okay, and this is because we're increasing the number of collisions. So you imagine if you have some powder that's gonna, or for example, okay, so like flour silos, grain silos, right? We have to watch out for grain silos because they'll blow up, and they'll blow up because grain is a hydrocarbon, and that has combustive possibilities, right? They mix with oxygen and they'll combust, they'll blow up, boom, no good, right? And so, but when the grain is all just sitting there in a pile, the only part that can reach oxygen is just the outermost layer, okay? Not very combustible. If it happens to catch on fire, it'll burn very, very slowly. All right. Now, the problem comes when that grain and that grain silo is dispersed, aerated. It's spread out through the air. So now, because you've increased the surface area of those grain molecules and their connection with the oxygen, you'll have much more possibility of an out-of-control reaction and then it explodes. Okay, and so if we can change the physical state so that we have more collisions, just by the mere fact that there are more collisions, there's more of a chance for a successful collision, and then therefore more reaction will occur. All right, so that's kind of what we're after here. So if we can change the solids to liquids, if we can dissolve them, they'll react better. Or if we can even like convert them into a gas, they'll react even faster. All right, and that's just generally because there's more collisions. Okay, so changing the state of matter or changing the surface area, those are the two things we're talking about here. Okay. Reactant concentrations. Now this makes sense. Okay, if you have more reactants, there's more likely for those collisions to occur. And they use this interesting example here on the right, on the ups, or the top picture here, they've got steel wool. Okay, and steel wool, it kind of looks like wire mesh. All right, and so it'll burn in air and it'll become iron oxide. All right, and when it burns, it kind of forms this kind of cool little sparkler effect, like with this fire that kind of slowly travels up the steel wool. If you take that steel wool, okay, and you burn it inside of a 100% oxygen container, it burns really, really fast. Okay, and it just creates like a little mini fireball and goes, and then it's done. Okay. And so that's essentially what we're doing here. We're increasing the concentration of oxygen. In regular air, oxygen is about 20%. Okay, so that means only 20% of the collisions of oxygen with the iron have the possibility of being a successful collision. All right, so or 20% of the air molecules colliding with the oxygen have the possibility of being a successful collision. In the container with 100% oxygen, it'll burn a lot more vigorously because we have all of the molecules hitting the steel wool have the possibility of a collision. Okay. Next one here is temperature. Okay, we know temperature is really just a measure. It's proportional, right? It's proportional to the average kinetic energy. Okay, this little Jesus fish means proportional to, and then average kinetic energy. So as our temperature goes up, the average kinetic energy goes up. Okay, and so if we can give these things more kinetic energy, then two things happen. Number one, there'll just be more collisions because they're moving faster, and so they'll hit more often in the same amount of time. And then number two, they'll also have more energy, so that when they hit each other, they'll have more possible collisions. All right. Or their collisions will have enough energy to overcome the activation energy, and so you have more reactions. Okay, more successful collisions there. Okay, and then finally here, last one for the video, is the presence of a catalyst. All right. Now, you've probably learned the definition of a catalyst, probably in like freshman biology, maybe Chem 1 or something like that. The presence of a catalyst affects the rate of reaction without being in the overall balanced equation. So, and it's not included in the overall balanced equation because it's the same as a reactant and as a product. And so it cancels out on either side, just like a variable in an algebra problem. Okay, and so this catalyst enters the problem, okay, and then it's going to change the type of collision that occurs. Okay, so in bodies with enzymes, essentially what happens is you've got some protein like this, okay, that might be shaped, and then what it'll do is you'll have some enzyme, okay, that'll come in and change the shape of this, so it's more likely for your collision to occur. Okay, and so when this guy comes in, it'll more likely to fit into this spot rather than this little tiny hole here or something like this. This isn't a great example. Okay, but essentially what happens is these catalysts are going to change the type of collision. So maybe it'll hold them in place. So like instead of both things bouncing around with the chance of hitting each other, it might get them stuck in one location so that it can't move. Okay, but what it does, essentially, we'll talk a lot more about catalysts as we move on, but this is really what you need to know. They affect the kind of collision, and they change the mechanism, and by changing the mechanism, they're changing the pathway, and so therefore you have you either increase the number of successful collisions by either changing the amount of activation energy needed or increasing the amount of correct orientations that could be possible. All right, so that's essentially it for what we're talking about in this video. Stay tuned, do your practice problems, let me know if you have any questions, and I'll see you on the flip side.